Shall I start? Welcome back for the second session. So that's a typical flow chart of any MD simulation. So let's go through the flow chart. What is that? Define the interaction potential and molecular topology. That means whether it is a LJ potential or Hertzsprung potential, you can give that, and that initial geometries of the molecule or the system that you have given. I mean, okay, that you have to give. Then assign the initial position and velocities. Compute interatomic forces. Mainly interatomic forces means the non-bonded forces, right? Okay, the hydrogen bond interaction, the van der Waals interaction, uh, the Coulomb interaction, those things. Then move the atom according to the equation of motion. Because as I said that this MD simulation is nothing but integrating the Newton's law of motion for a main body system. Then after this motion, you have to restore the molecular geometry, and then you have to compute this energy, temperature, pressure, etc. Whatever the thermodynamic properties are. Then you have to store these things with respect to new partition coefficient or like the new ensemble, and you have to do it until unless your end time has reached. So this is a very general thing. Now again, all these are basically programmed in the open source or the licensed packages of MD. So again, so first we start with the equation of motion. So again, it's a Newton's second law of motion, and so equation of motion in MD simulation involve the position and velocity of each atom of the system. These equations are typically represented as a system of coupled second order nonlinear ordinary differential equation because it's a F equal to m d2x dt2, right? Okay. And the forces acting on each atom of the system are calculated using the prescribed interatomic potential that we will see, which describes the interaction between atoms based on their position in the space. So we have seen 3-4 of them, like the Hertzsprung potential, the Sutherland potential, square wave potential, LJ potential. Those are basically defining the non-bonded interactions. Now, in this, again, when we are dealing with this molecule, we have the other type of interactions like bond, angle, dihedral, improper, etc. Those will also come into play along with the non-bonded interactions. And these forces are then used to update the position and velocity of each atom according to the Newton's law of motion, because the potential energy that is related with the force that we have seen, that the force is nothing but the negative spatial derivative of the potential energy. Okay. So for the first case, we see the Verlet algorithm. So Verlet algorithm is nothing but the Taylor series expansion. Okay, Taylor series expansion of the position vector. So let's say our present position is t rt, and I want to move my next time instant, which is r at t plus delta t. As it is a very small deviation, the Taylor series is only applicable for the small deviation, right? It cannot go for a very large deviation. If it goes, then the stability criteria will be violated. So that delta t or the small time increment, what will be the position that we can express with respect to the Taylor series expansion. First term is obviously the present position. Second, we have the dx dt term, so which is nothing but the velocity. And third is the d2x dt2 term, d2x dt2. So d2x dt2 is the acceleration, that is nothing but force times force divided by mass of the particle. And the other terms we generally neglect. Similarly, for the backward case, we have this expression. Now, if you add these two expressions, 1 and 2, then you can get the updated position with respect to the present position, the previous position, as well as with respect to the force. Similarly, if you subtract these two equations, you get an expression of the velocity. So this is called, although this looks very simple, but when you do the when you apply this algorithm for the many body problem, the computation becomes really challenging as well as very much time consuming. So this is known as the Verlet algorithm. Okay, so some discussion about the velocity Verlet algorithm, that the position of each atom at the next time step is updated using the current velocity and force that we can see here. This one. Okay. And this two-step process ensures that the system evolves according to the Newton's law of motion position propagated using positions as well as acceleration. It can also handle large time step. That means you can increase the delta t while maintaining the stability and preserving the energy of the system. This Verlet integration algorithm are widely used in the MD simulation because of their numerical efficiency. Other than the Verlet algorithm, several other schemes are available. One of them is the leapfrog integration. So in the leapfrog integration, the advantage is that we do not compute the position and velocity at the same time instant. We do not compute the position and the velocity at the same time instant. Let's say if the position is computed at each and every grid point, then in the mid of the grid point, we compute the velocity. So it has some certain advantages that has been observed over the time. Okay. So the position of each atom at the next time step is updated using the current velocity, while the velocity is updated using the previous position, current, and the next forces. So these are the particular expression, and this two-step process ensures the system evolves according to the Newton law of motion. Again, Newton law of motion, that expression is divided or expanded in the Taylor series with for the many body system. Okay, so there are some differences between the leapfrog algorithm and the velocity Verlet algorithm. That the first one is that the velocities are not calculated at the same time as the position. Okay, whereas in the velocity Verlet algorithm or the Verlet algorithm, we have the both positions and velocities are computed synchronously. Time reversal invariant and explicitly incorporate the velocity, eliminating the issue of the first time step. It has some advantage due to the time reversal invariance and second order inaccuracy. And but this velocity Verlet algorithm is widely used for the simplicity. Okay, for this one, it requires the future or subsequent position to find the current velocity. Sometimes it becomes difficult when the systems are not exactly at the grid points. Okay, time invariance. If you can see that these expressions, when you reverse that, you will not get the exact same position. That is the invariance concept. Okay, that means here the energy is not exactly conserved for each and every node. That is the invariance concept. Okay, so now here also, like your MC, okay, monitor. So this like MC, here we can use NVE concept, NV ensemble, then NVT ensemble, NPT ensemble, as well as the MuPT, but normally people use either NVT or NPT. Now, for the macroscopic thermodynamics, okay, what we know that we have four variables, right? What are they for a system? Okay, moles, yes, pressure, temperature, volume, and moles. So whenever you fix that number of moles, volume, and temperature, what can vary? Okay, pressure. That means here that in this case, the system volume will not change. Now, if you want to validate the force field, or let's say if you want to equilibrate the system, okay, most cases we measure the density first, right? If we are doing the liquid simulation, if we are doing a multi-phase simulation, let's say the gas and the liquid, then the validation of the density is not required. But whenever we are doing a purely liquid simulation, we try to validate the density of the system first. That time, NVT is not okay, is not a good option, because that time we have to go for the NPT, because in the NPT, what is there? Number of moles, pressure and temperature, they keep at a constant range, and what will vary? Okay, volume. So if you do the NPT simulation for the liquid system, then ultimately, based on your simulation condition, the simulation box either will shrink or it will expand, right? And then eventually you get the optimum volume. Based on that, you can get the number density. Once you get the number density of the system, you can convert the number density into the actual density of the system. So specifically for the liquid simulation at the equilibration stage, people generally use the NPT. Once the density is attained, then they switch to the NVT for the production run. But if you are doing for the multi-phase simulation, okay, let's say you are doing the gas absorption in a surface, or let's say ion interaction, lithium ion interaction with the electrode, that time the best suitable candidate is NVT. That time, because you don't need the density, right? You need a fixed volume where you will measure the interaction first. So based on your what you need, what is your end goal, you have to choose the ensemble, right? This one is clear. Okay, so so some basics of the ensemble. So these are all given to your note. So this NV stands for microchemical ensemble, where the number of particles, volume, and energy are conserved. It models the isolated system with no exchange of particles, volume, or energy with the surrounding. Okay. NV ensembles sample the microchemical distribution where all accessible microstates with a given energy have the equal probability. There is a key limitation is that the experimental systems interact and exchange energy with the surrounding. Therefore, these NV ensembles do not capture the effect of temperature and the pressure control. So that's why in most of the MD simulations are doing with either the NVT or in the NPT mode. Then this NVT ensemble that sample the canonical distribution where the probability of the microstate depends on the energy following by the Boltzmann distribution law. It assumes the constant volume, so it does not capture the pressure effect. Now, there is a concept that the volume is constant, but it is not exactly the constant value. it will fluctuate with a particular mean, right? When we have this temperature is constant, that means temperature will not be exactly the constant. It will fluctuate with respect to a particular mean. Now at the start, in the first half of this lecture, but I said that we need the thermostat as well as the barostat to keep our system, to keep our system stable. Now, during our simulation, during our MD simulation, the molecules are moving. It is colliding with each other, and therefore the temperature is increased. But in the NVT simulation, my temperature will remain constant. That means with a certain range. So what is the control mechanism I will use? Here. Okay, thermostat, right. So here for the NVT simulation, if your script incorporates the barostat, then just put those values equal to 0. It will be the NVT script. Okay. And for the NPT, you need to keep the pressure within a certain range. You need to keep the temperature within a certain range. That's why you need both thermostat as well as barostat. Okay. So NPT, it mimics the experimental system in contact with a heat bath as well as the barostat, and the thermostat regulates the temperature while the barostat modifies the volume to maintain the target pressure. NPT is more realistic than NV and NVT for modeling condensed phase system. So the physicists say condensed phase, the chemical engineers say is the liquid phase. That's a fancy term for the physicist. We are working on the condensed matter, right? So for the liquid system, NPT is more reliable because you can have a ready-made parameter, ready-made descriptor to validate, that is the density. For the solid, it's not like that. Okay. For the solid, if you have the solid, then it is preferable to go for the NVT, because for the NPT will distort your system. Okay. Okay. Mu PT, that's not exclusively useful. Okay. Thermostat control temperature. So what is it? Okay, what is a thermostat? A thermostat is a modification of Newtonian MD scheme designed to generate a statistical ensemble at a constant temperature. It helps to simulate, it helps to match the simulation condition with the real world experiments, because it will not allow your system temperature to go unbound. It will not allow. But okay, obviously you need to place your system, you need to place your molecule in such a way that it should not go unbound. It has also some limitation. As I said with the hexane example, that you cannot place two hexane molecule with another, because at that time so much energy will be created at the very beginning that your system will be unstable and the thermostat will fail. It should have some distance. Let's say for the pack mode, the default distance is 2 angstrom difference. Anyway, you can give more than that one. Some examples of that thermostats are Anderson thermostat, Langevin thermostat, Berenson, Noseuver. Each and every one has its own pros and cons. Okay, so this is the Anderson. So here the advantage is that it leads to the canonical distribution. Do not capture, but the disadvantage is that do not capture the true dynamics of the system due to the external influence with the particle in the system. Now, whatever this thermostat and barostat, now for modern day simulation packages, you don't need to write those code. The keywords are already available for the NAMD, LAMPS, GROMACS. You need to just incorporate them. And then those thermostat and barostat will work. Okay, depending upon your system. So here the velocity distribution it follows this Maxwell-Boltzmann distribution, and at the simulation start, the distribution no longer follows the Boltzmann distribution due to the collision between particles and heat bath. Velocity of randomly chosen particles are refreshed after a certain interval. So they follow the Maxwell-Boltzmann distribution at any temperature. Similarly, this is the Langevin. It also, the advantage is also leads to the canonical distribution. The cons is it affect the that disadvantages. It affect the system dynamics. The Berenson, in most of the cases, either we use the Node-Hoover or we use the Berenson. So the Berenson algorithm, it mimics the weak coupling of first order kinetics to an external heat bath with respect to this condition, and the strength of coupling, it can be varied. So when we go to the GROMACS simulation, we will see that this strength we have to define other than our other than our default value. We can basically change this strength of coupling, right? So let's say for equilibration purpose, the coupling time can be taken as 0.01 picosecond, but for the reliable equilibrium runs, it can be taken to the much longer. Then this is the most famously used, that is the Nose-Hoover thermostat, and it also follows the canonical ensemble. Okay, and modify the equation of motion to allow the MD system to interact with the thermal interval at a constant temperature. And this neta, that is the damping factor, which we can always define during our run script. Okay, the advantages are the Nose-Hoover is known for the robustness, ensuring that the system temperature remains constant throughout the simulation. And this thermostat is efficient and does not require the addition of random forces. Okay, the disadvantages are this is more complex and it introduces the stochasticity or the randomness into the simulation, which can affect the dynamics of the system. And therefore, it can potentially lead to the defined result when comparing the multiple simulation with different random seed. So that's why when you generate a new geometry and start, the triplicated simulation, always change the random number as well. Okay, to get the different seed. Okay, so now so far up to this one is for the thermostat. Now for the pressure calculation, we go for the Virial theorem. Okay, and from there we can go to the barostat. So this Virial theorem, as you know that so this is the Virial equation of state. Z is PV by RT. Okay, so from here we can compute the pressure. So the Virial theorem is used to calculate the pressure in the MD simulation. The pressure can be obtained at the boundary of the system using the Virial theorem of the Clausius. It provides the method to determine the pressure at homogeneous system in the equilibrium. Basically, we do not measure the pressure of each and every atom. Okay, rather than we measure the pressure of the entire simulation box. So the advantage is it provides the fundamental relationship between the kinetic and potential energies, allowing the calculation of the pressure in a MD simulation. It offers a theoretical basis of understanding the behavior of system and is widely used in the StatMed. Now, the disadvantages are in systems not in equilibrium or that is not the homogeneous, Virial method can lead to the ambiguous result. Additionally, for the small system of arbitrary boundary condition, and these interactions are neglected and which can result some error. So this indicates that the method of stress calculation maybe more general and the virial method in the certain cases. So this is all about the theory, nothing. Okay, so that is the mathematical form. Okay, now we come to the barostat. So barostat regulate, I mean, same way when you do this NPT simulation, you need to regulate the pressure. So this barostat regulate the pressure by adjusting the volume of the simulated system. This is achieved by scaling the coordinate of each atom by a small factor and thereby changing the size of the system because you need to attain the density. To use the barostat, ensure that the system within that the pressure within the system remains constant, contributing to the stability and accuracy of the MD simulation. So this is the example of the Berenson, okay, Berenson barostat. Okay. So there are some advantages and disadvantages as well. It is Berenson barostat, it is computationally efficient and requires less computational resources. And its disadvantage is that it's not accurate and does not yield the exact NPT ensemble. This can lead to the error to the simulation result. And for the non-equilibrium MD, this algorithm is not suitable. Okay, there are some limitations with the MD simulation that I have already discussed at the start of my lecture. So I'm not going to read it again. Okay, next is coming as the interatomic potential. Okay, so far while discussing this. Okay, so while discussing this potential energy function, we have mainly considered this non-bonded potentials. But when we are discussing with the molecules with respect, I mean, when we are discussing with respect to the molecules, we have our bond, angle, dihedral, improper, along with this non-bonded interactions, right? So all those will come under interatomic potential. So basically, what is this one? This is a mathematical function that defines the interaction of atoms in the system. When these atoms are bonded or connected with each other, we get the bonded, angle, dihedral, improper interaction. When they are not bonded, we get the non-bonded interaction like the Coulomb interaction, Van der Waals interaction, etc. These potentials are basically, I mean, the development of potential. These potentials are basically transferable. That means when these potentials are being generated, they are being generated with a set of compound by doing multiple DFT calculation. And but those potential values, I mean, those values can be used for the other systems that based on that, we do the molecular dynamics simulation. So the development of the transferable interatomic potential that work well for defined materials and systems of interest is an ongoing challenge. It enables the accurate prediction of interatomic forces, allowing high fidelity dynamical and the statistical simulations, which can be executed up to 20 million times faster than the density functional theory that we will discuss. Okay. So the components are basically the bonded terms like chemical bond, angle, dihedral, and improper. And non-bonded terms is the Van der Waals and the electrostatic. So these are the main. Additionally, some more things can come, like the may include the many body terms beyond, that is beyond pairwise, and empirical or physical based functional forms. Okay. So when two particles are connected with a line, we call it bond. When it is three, okay, what do we call? Angle, right? So what is the dihedral? Between two planes, right? Okay. So if it is a 1, 2, 3 and 2, 3, 4, then those planes, that is okay, that is the dihedral angle. But is the improper? If we have 1, 2, 3, 4, then keep the 2 outside. 1, 3, 4 is making one plane, right? And the angle between the 2 and that plane is the improper, right? Okay. So okay. So this is the typical structure of the force field. This is a typical structure of the force field where this is the potential energy function. Recall that the potential energy function is used to calculate the force. F equal to negative of du dx. That is, now this has the bonded interactions, angle interaction, the dihedral or torsional interactions, as well as the non-bonded interaction. Among the non-bonded interactions, we have seen that the LJ potential is most accurate, and this is the Coulomb, right? In the Coulomb, we have this Qi and Qj. What is this Qi and Qj? Can anybody tell me? Charge, right? The Qi and Qj are basically the partial charges of each and every atom. And how do we obtain it? By 4 methods that I discussed, either by the quantum chemical calculation, or by the calculation, or by from the single point calculation of a crystallographic data, or from the PDB file. So those charges will be used here. This Rij is, as we are considering the pairwise distance, that is the Rij. Similarly, these are the epsilon and sigma. These are basically the Lj component, Lj parameter. And these are the bond angle and dihedral. Now, this expression, you can see that bond is Dij minus Dij 0. Theta ijk, obviously angle is a three body interaction. So theta ijk minus theta ijk 0. So can anybody answer me that what is this Dij and Dij 0? What is the difference? Hmm? Yes. Yes, one kind of. Which one is equilibrium distance? Yes. Kind of. Yes, you are telling something. So that zero. We fix that. We're fixing that molecule, measuring from that molecule to the other one. Kind of. That's why we are doing n into n minus 1 by 2, as we said, the number of interactions we have to manage. That one we are fixing and then calculating for the rest. Yes, from the equilibrium point, right? Okay, good. Okay, so basically, when you optimize this, when you optimize the geometry in the QC, quantum chemical calculation, have you seen that what is the output of Gaussian? Let's say I have optimized hexane or ethanol or methanol. What is the output? I get a log file where the optimized coordinates are present, right? Let's say it's like this way. Let's say C, 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 then something x coordinate, y coordinate, z coordinate, right? And at the end of that, we have this 1, 2, 3. Like this way, we get that. So, what are this? Now, this is the coordinate of C. And this C and C, sorry, 1. So second C and the first C, they are connected with respect to a bond. Third C and second C, they are also connected with respect to a bond. When they are connected with respect to a bond, based on their x, y, z, the distances are observed, right? What is the Rij? Square root of x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square, right? So whenever you are optimizing any kind of geometry, you get this Rij, or we can say that Dij, etc. That is this one. That means your system. Now what is this one? This distance is their equilibrium bond length obtained from the force field. So how people generate the force field? Okay, so let's say I want to create a force field of alkanes. So what the researcher will do, they will do multiple DFT calculations of a number of alkanes. Let's say methane, ethane, propane, butane, etc. They will do that, and they will check what is their bond length range of C and C. Maybe for ethane, it can be 1.41 angstrom. Let's say, just example. Okay, for propane or for butane, that may be little bit vary. So by taking their average length or average range, the researcher will give that this C and C allowable bond length is 1.41 angstrom. Based on that CH, OH, etc., that they create a database. Similarly, for the angle, as 1 and 2 are connected, 2 and 3, 3 are connected, so there can be an angle can be formed. Similarly, by doing multiple DFT calculations of all the alkane, the angle could be formed. And by taking their number of calculations, they will put one average value or the range, that if this happens, CCC, then this kind of angle it can have. So that's the equilibrium angle. Similarly for the dihedral, similarly for the improper. And after doing n number of computation, they just put all those values in a notepad file and distribute to the user. Okay, that is the equilibrium length, equilibrium angle, dihedral of those n number of alkane systems. That is the allowable. Now, when you do your calculation, you derive, you optimize your molecule, and then calculate the deviation from the equilibrium. That's why whenever these force fields are being generated, that is, it has been mentioned that this is applicable for this one. There are the Amber force field, like GAP, generalized Amber force field. That means it can be applicable for any kind of organic system. There is a generalized charm force field, CJNFF, that is applicable for any kind of charm force field. But for the other type of proteins, other type of nucleic acid, specific force fields are present, because the researchers, when they have developed those force fields, they did with the certain type of calculation, quantum chemical calculation, and give these values. Now, whenever you have a certain type of protein or nucleic acid in those range, and optimize their geometry. That time you can get the deviation. Okay. So normally when we are doing these organic simulations, organic molecule simulations, we use the gap or CGNFF or like OPLS, which is applicable for the any kind of organic system. But for the biomolecule system, particular force field are useful. You cannot randomly change with one force field to another. You will get drastically different result. So those things, now this is clear, right? And these are basically these LJ parameters. They are basically defined. You use the mixing rule to get that epsilon ij or sigma ij, etc. Clear? And this one, Qi and Qj, they are basically your partial charges. So basically, when we get this bonded energy, the interactions are 1, 2, angle is 1, 3, torsion or like dihedral or improper, that is the 1, 4 interactions. That means first atom can interact with the fourth atom. Here angle means first atom can interact with the third atom. Bond means first atom can interact with the second atom. And this Lj and Coulomb, that is basically the non-bonded interactions. So this is a typical formulation of a force field. Now, how these expressions have come? Okay. So now that the bond stretching expression, if we take the Morse potential, this has the form, and when you plot that, you get this. You get this green curve. It can be approximated with respect to the Hooke's law, whose plot is here. So approximately the well depth is exactly attaining. The well depth, it is exactly attaining. So the bonded interactions we can obtain from this expression. So this is again the bond stretching parameter. Angle, again, it can be obtained with respect to the same as this Hooke's law angle that attains the same depth of energy. Similarly, the dihedral, it can be attained with the Fourier expansion, because you can see that it is attaining the same phases as well as the same minimum. Then again, that is the improper, and this is my LJ part where the mixing rules are added. Mixing rules are added to get the unlike interactions. Okay, and this is again the electrostatic part, the Coulomb part, which is attained with respect to this this formulation. Clear? And here the dielectric constant, you can take 1 for the vacuum, 4 to 20 depending upon the protein core, and 80 for water. But again, this part is generally defined in your particular user guide. Most people, they take the default value. They do not change. Okay, this is done. And then the attractive interactions, that has some dependency with respect to the distances. Okay, let's say if you have the charge interaction, there is the attractive interaction. The dependency is inverse of the distance. If it is a charge with respect to the dipole, it is inverse of the square of distance. If it is a dipole interaction, inverse of cube of distance. And then dipole and induced dipole, it has RH to the power 6. Okay. One special case of interaction that we usually see in the MD simulation is the H bonding. Okay, hydrogen bonding. That these hydrogen bonds are extremely important for any kind of structure, and some force field have special functional form of treating the H bond. Then the majority of force field only rely the combination of electrostatic and the van der Waals term to reproduce the H bond. So generally, we take the force field formulation here in this form. So we do not mention the hydrogen bond separately, but we calculate the hydrogen bond and the strength of hydrogen bond in the post processing. That means after the running of the simulation. Okay, and again, your geometry will play a role to determine the strength of the hydrogen bond. Let's say for this case here, the oxygen is pulling the electron cloud towards itself. So okay, so therefore the hydrogen bond strength will be more. But here, this water oxygen, I mean, this is the position is somewhat different. So therefore, the interaction strength, the vector, it will not be the 100%, but the cos component will be here. So obviously, as the cos component is here, that time the interaction strength or the electron cloud is somewhat higher, and the interaction will be. So by maintaining various position of the atoms, the hydrogen bond strength will be changed. And generally, we take this hydrogen bond within this range. So when we calculate the hydrogen bond with respect to the VMD or any other post-processing software, we generally define the ranges as well as define the angle. Based on that, the hydrogen bonds are computed. Okay. Now again, this 1,2 is bond, 1,3 is angle, and 1,4 is the diagonal. Now there are, I mean, some famous force fields are like OPLS, AMBER, and CHARM. It takes different fraction. Let's say whatever these electrostatic interactions are, OPLS takes only 50%. Although you can change it, you have the lever to change it. The CHARM, it takes 100% of the electrostatic interactions as well as the van der Waals interactions. But you can always change. There is the option. These are basically the default values. Okay. So the limitations. Now, when we compute this interatomic potential, it has some limitations, like the classical interatomic potential often exceed the accuracy of the simplified quantum mechanical methods, but they still rely on the approximation and the simplification. Next is the traditional interatomic potentials are typically parametric because a set of values, equilibrium values, are already defined. You are just calculating the deviation from the set of defined values. So that meaning they are already developed by some other, optimized with a fixed number of physical terms as well as the parameters that I have explained here. So, okay, let's say you are doing some simulation of the alkane and you want to use a particular force field. So if those force field parameters are based on the alkane, then you will get very good result. But if the force field parameters are based on, let's say, alkane, alcohol, ketone, etc., all the things, then those equilibrium values are only the average value. Your simulation will not get that much accurate result. But anyway, the force field development is not everyone's job. Let's be practical. Okay, there are specified groups who develop the force field, and those upgradation require periodic. I mean, those require periodic upgradation. But mostly, we all deal with the application. So whatever someone has been developed from the UIUC group or like that the Amber group, okay, the parent Amber group, we use that and get our result, right? So now, yes, the same thing is that the traditional interatomic potential may not be able to accurately describe the behavior of the material in the non-equilibrium process, like non-equilibrium MD, which is not the part of this discussion. And this can be a significant limitation for the simulating materials with complex bonding as well as dynamics. Let's say so. Now, one of the practical challenges is uh, simulating the cross-link structure. Whenever you have a cross-link structure, I mean very complicated cross-link structure, the cross-link joints, those connections, they are not completely movable. Okay, so using the existing potentials or existing port field, that can give erroneous result. But there are ways to overcome it. Either run very long simulation, or you can do it the umbrella sampling, etc. But those are the advanced technique. So in those cases, I mean the cross-link structure, this whenever this complex bonding or dynamics come, then the existing force will have very significant limitations. To overcome that, some advanced potentials are also present. First one is the reactive potential. Although I am not doing any simulation on this reactive potential, Professor Banerjee has done extensive work on this reactive potential. So the thing is, although the concept of MD is to determine the non-bonded interaction, that is there. Okay, MD does not explicitly tell that the bond breaking or the bond formation phenomenon. But this ReactFF or this reactive force field, it includes the bond breaking or the bond formation phenomena, but with a certain cost. What is that cost? Is that if your reaction, let's say, is happening at 330 K, for the ReactFF part, it will increase the temperature at least up to 10 times or something like that, high temperature, and then the bond breaking or the bond formation phenomena has been observed. But for that, you cannot use the simple potential. You have to use this reactive potential. So one such thing is available in this ReactFF software. Okay, so it's a licensed software, and Professor Banerjee has been widely developing this kind of reactive force field simulations. But that comes with a certain cost of increasing the temperature, which sometimes is difficult to validate. Let's say into the temperature, see those bond breaking and these events happening. Then only the high entropy reactions. The final things you cannot observe. So you will see. The trajectory may not be that high. You get the and okay, sometimes it is difficult to convince the reviewer. Yes, your experimental work is happening at 330 Kelvin. Why you have increased the 10 times? It's very difficult. Yes, because you never know. Yes, that's very difficult. But yeah, work is ongoing. Again, the reactive potential includes the charge optimized many body potential and reactive force field or ReactSFF. There is a particular software package is present, and then you can do all your simulation. And reactive potentials are used to model the chemical reactions, catalysis, combustion, and other reactive processes in material science, chemistry, as well as, although it is written in the biology, but I don't think that that is explored. Okay, so reactive potentials are highly accurate and transferable, allowing for the simulation of complex systems and modeling the condensed phase chemical reaction. That means the liquid phase chemical reaction. Okay. So some differences that the reactive potentials enable the simulation of chemical reactions and bond breaking events, while the traditional interatomic potentials focus on the modeling on the material properties, structural as well as the transport properties and forces between the atoms. And reactive potentials allow the exploration of entire potential energy without any bias. So it provides a more comprehensive understanding of the chemical processes. And the traditional interatomic potentials include empirical or the semi-empirical potential, while this reactive potential include the charge optimized many body potential and reactive force field. Okay. Then next is the polarizable force field. So this is the huge debate whenever people are working with the ions. Let's say myself is working with the ionic liquid and diputative solvent, so that involved ions, and there is a huge debate that whether for this kind of ionic system, whether we use the non-polarizable force field or we use the polarizable force field. So the thing is, what we do basically, we generally use the non-polarizable force field, validate some experimental result of those systems, and with that validation, okay, we move on. Okay. So although the polarizable force fields are present, but so far, if you read the research paper, that mostly the polarizable force fields are licensed. Mostly, I'm not sure whether they are open source or not. And people who are working with a Material Studio, etc., they get the access of that one. Okay. So, okay. So it includes that the inclusion of the polarizability in the MD simulation, especially for the homogeneous liquid like water, although it says water, but mostly for the ions. To increase the accuracy of the in modeling the material properties and chemical processes. This allows the dynamic redistribution of charge between atoms and response to the local chemical environment, which is particularly beneficial for the modeling system, such as water as well as proteins. Unlike the classical force field, the implicitly include the effect of the polarizable force fields explicitly model the polarizability using these root particles or the fluctuating charges. Okay. They are widely used in the biomolecular simulation more accurately to represent the electrostatic interactions, particularly the systems where the electronic polarization plays a significant role, mainly the movement of the ions. Okay, again, some differences are there that you can read out. Obviously, the addition of the polarizability is the key factor in this polarizable force field. Okay, there are some differences between the reactive force field and the polarizable force field. So for the reactive force field or reactive potential, it is designed to simulate the chemical reaction and the bond breaking phenomenon. That is the specific purpose. But for the polarizable force field, it is more accurately modeled to for the behavior of molecules, particularly the biomolecular system, explicitly considering the polarization of atoms and molecules. It explicitly, the reactive potential. It is dynamic redistribution of charge between atoms in response to the local chemical environment. And here it is explicitly model the polarizability, allowing for a dynamical redistribution of charge between atoms and response for local chemical environment. It often involves a complex situation, and the bond breaking or bond forming phenomena can be observed on the fly. Okay. And it focused explicitly on the modeling of the polarizability and the dynamic redistribution of the charge between the atoms. Next is the ab initio potential. So probably you have already gone through it. So ab initio potentials are derived from the first principles, right? So what is the first principle? Can anybody? Yes. Okay. So integrating out the electronic charges, electronic degrees of freedom, and give the energy as a function of the spatial coordinate of the ion. So basically, this ab initio potential, what it says that, remember in our potential we have this term r minus r naught. So now for this, for the classical force field, we have a set of r naught values listed in notepad file. But for the ab initio part, for the ab initio potential, these are computed real times. That makes this kind of potential very slow. So these potentials form the basis of classical MD simulation, determining the forces experienced by the atoms and specifying the material properties. These are crucial for the high pressure application, strain, and the phase transformation simulation in metals. And these potentials provide a balance between high fidelity and high speed, leveraging the computational power for the development and application. They are developed through extensive calculations, like mainly DFT calculations, and are used for highly scalable simulations. This ab initio model potential method integrates with the effective core potential method, showing the efficiency of simultaneous calculations and being very close to the frozen core level of approximation. So what is frozen core level of approximation? DFT the theory. What is the frozen core approximation? Okay, what is the von Oppenheimer approximation? Right. Okay. So now that the frozen core approximation is that when your atoms is having more number of electrons. Let's say your lanthanide series or your actinide series, it has more number of electrons. Now, when it has a more number of electrons, the lower orbital electrons, they do not move to the valence band, but they do not perform any kind of interaction. They basically sit idle. Whatever the interactions are happening at the outer shells or the outer orbitals. So therefore, to make the computation faster, if we assume that whole set of electrons, then it will be very slow, computationally slow. So therefore, what we assume that the lower orbitals are frozen. That means those electrons, they do not move. Like whatever the von Oppenheimer approximation, that means we are excluding the nucleus that has been extended to the higher orbitals. and we only keep the outer valence electrons. That is mainly applicable for this the lanthanide, actinides, etc. And that significantly fasten the computation. So similarly, once we are doing this ab initio model, only consider the valence band electrons at the outer shell or the outer orbital. We do not consider this 1s, 2s, or 2p, etc. unless it becomes a carbon. Okay. So that is one kind of analogous to the frozen core level of approximation. Have you done this Gauss view, right? But you know, right? Gauss view. So in the Gauss view, if you open that GAIN or GAIN ECP or ECP, this kind of keywords that basically represent the frozen core approximation. Okay. So you can just search if the Gaussian is here. Okay, draw a structure of, let's say, okay, europium, and then you can see in the DFT, GAIN ECP or ECP, etc. Those are basically the frozen core approximations. Okay, moving on. Again, there are some differences between this ab initio and the traditional interatomic potentials. So ab initio potentials are derived from the first principles, and it has been periodically updated with each and every step that makes this kind of simulation is really slow. Taking into account the local chemical as well as the magnetic effect, while the traditional interatomic potentials are empirical based on the fitting of the experimental data. So ab initio potentials, as these potentials are iterated with every, these potentials are upgraded with the DFT calculation. At each and every step, they are generally more accurate, because that is, those potentials are not taken from a set of notepad values. That has been with your simulation, those are being updated. And they are derived from the first principles, take into account the electron structure, while the traditional interatomic potentials are based on the empirical fitting that someone has done for you and published as open source. Okay. There is something called hybrid quantum mechanical or the molecular mechanics potential. A hybrid QMMM potential integrates the quantum mechanics as well as the molecular mechanics methods, allowing the accurate treatment of the small region with quantum mechanics and rest of the system with MM, enabling the study of the chemical process of the complex environment. In the electrostatic embedding scheme, the partial charges of MM atoms surrounding all QM atoms are all approximate to electrostatic interaction. That means the partial charges are calculated, allowing more comprehensive treatment of electrostatic effect in the hybrid method. The potential, this is not required. Okay, it has been used to improve the potential for the mean force in the quantum mechanics or oblique molecular mechanics studies of chemical processes in the condensed medium like liquid system, demonstrating their utility and capturing the energy of complex system. Okay, so now let's say how much time is required. So this is one simple idea for a 1500 atoms. Then there are 10⁻⁶ pair of interacting atoms. If you do that, and non-bonded interactions, that is order of n squared. That means 1500 times 1500. And non-bonded interactions require most computational time, because the bonded interactions can only go up to 1, 2, 1, 3, or 1, 4. But non-bonded interactions can go up to n cross n-1 divided by 2. Right? So that can go hugely. So objective is to compute the non-bonded interactions in a faster manner. So several algorithms are there to compute that non-bounded interactions. So the first one is using the cutoff. Let's say this is my very crude way to describe the LJ potential, where this attractive part theoretically it will go to the infinite distance. It will not be zero. But since we do the molecular dynamics simulation with respect to a box, it has to end somewhere within the box. That's why what we do, we create a forcing function. We create a forcing function that force that interaction to come to zero at a finite distance. Okay, for each and every simulation packages, the forcing function is defined, but you have to choose that when, from where this forcing function will start. Okay, so it has to start here or here. Okay, whatever the distance from distance where it will start, that you have to choose. The forcing function is already being defined unless you create a new forcing function that again comes to the recompilation of the software packages. So we don't do the recompilation of the software packages. What we do, we just apply them. So therefore, we take the default forcing function of the software package. Again, when we do that, when we use the force, when we use this forcing function, we basically truncate our non-bonded potential. That is given here. Okay. Next is, so the non-bonded interaction is divided into two parts. One is the LJ, another one is the Coulomb. So LJ is considered, LJ is taken care of with respect to this forcing function. For the Coulomb, we use one technique that is called Ewald summation. Now, in the Ewald summation, in some cases, if we have used this MD part, then we have seen that whether we write PPPM or PAB, that means the particle mesh Ewald, or PPPM, what is the particle and particle mesh, right? So Ewald summation that has some acceptance in various molecular dynamics packages, whether you can use the PPPM just like the LAMS, or in the PAB just like NAMD or GROMACS. So it takes this Ewald summation is a method used in the computational chemistry to calculate the long-range electrostatic interaction in the systems with the periodic boundary condition. I hope you know that periodic boundary condition, right? It has been cleared in the MC, right? Periodic boundary condition, so I don't need to explain it, right? Okay. So in the PBC, we have a central simulation box and we create the images. So that central simulation box is your, there the long range interactions are particle. And their images, we create the mesh. So those kind of long range interactions are particle with mesh, right? So in the adaptation of Ewald summation in the GROMACS or NAMD is the PME, particle mesh algorithm. In LAMS, it is called PPPM, particle mesh algorithm. That means the long range interactions are calculated within the simulation box as well as with this image. In the image, we do not put the particle. Instead, we put its respective mesh. Okay. So this Ewald summation method involves separating the electrostatic potential into two parts. The short range part that can be calculated in the real space, that means particle, and the long range part which is computed in the reciprocal space, that means particle mesh. So in the real space, we have this particle and its image. This one. Okay, this one is the particle with mesh. So that's the long range part that is computed in the reciprocal space using the first Fourier transform or FFT transform. These two are combined to obtain the total electrostatic energy that we obtain this E equal to Qi Qk times some expression, some denomination are there, right? Okay. Again, the Ewald summation provides a more accurate treatment of long-range electrostatic interactions composed of simple truncation or direct summation method. It also converges rapidly with the size of simulation cell, making it with a valuable tool for studying the periodic systems with electrostatic interactions. And this is commonly used to calculate the electrostatic contribution to the potential energy of the system. It is an essential tool for accurately modeling the behavior of the charge or polar materials in the periodic boundary condition, okay, such as ionic crystal and the biomolecular systems. These are the different force field parameter that we require to obtain for defined type of things. All of them we have discussed so far. Some common all atom force field parameters. These are OPLS, amber, charm, Promax, amoeba, etc. These all of them are open source. Now, this amber, charm, okay, it has a n number of potentials in their repository. Okay. Shall we take lunch or then we'll move to the advanced lunch? Take a lunch. Because after that we need to learn the tutorial part, and I will give you some home tasks. Hopefully, in the evening you will do it, and tomorrow we will do the tutorial. 3 tutorial sessions.